Go back here. All right. Today is October 14th. We're going to look at conditional probability. There will be a quiz available from the end of class today until midnight tomorrow. You must submit your work for any credit. I got an email from somebody asking why their grade in my labs was higher than their grade in Blackboard. And I didn't take that much away for not showing work, but I think at the beginning of the semester I said there was no way you were getting full credit for anything if there was not supporting work. This time I will not look at any grade in my labs unless there is work supporting it in Blackboard. Did everybody hear that? I don't care what your grade is in my labs, I am not putting it into the Blackboard gradebook until you submit your work in Blackboard. I'm using the Blackboard gradebook to put it in, and I will not accept answers without work. Everybody hear that? I think we had said that on the first day of class going over the syllabus. I'm going to become much stricter in enforcing that. Homework 11.5 is due today. That's the probability with permutations and combinations. That next homework 11.6 will be due on Friday. That is what we worked on last week, the not or odds. 11.7 is what we're looking at today, conditional probability. 11.8 is expected value. Those will be the last things that we look at. Those will be due Wednesday the 21st, so exam 2 tentatively will be on the 23rd. We'll see how we feel after we go over a practice exam on the 21st, whether it'll, and where we stand, whether it'll be available from the 21st till the midnight on the 23rd, or from class time on the 23rd until midnight on the following day. Before we get started, does anybody want to look at, well, first of all, does anybody have questions about any of that? Or does anybody want to look at any homework questions?
The last one, the one that is due today, I worked on it. The last one, I tried to follow your method. I still could not get my answer right.
Okay, so the homework that's due today, the very last question. I like seeing you guys, but their toolbar gets in the way. I'm sorry. The homework that's due today, let's preview it.
Oh, today or tomorrow is due tomorrow. However, the last one we do it. The one that's like 10 questions.
Yeah. Oh, my computer unplugged. Let me plug that back in. Oh. It's not. Here we go. Question number 10.
Yeah, the last one.
Says a lottery, the top cash prize was 666 million, going to 3 lucky winners. Players pick 5 different numbers from 1 to 52 and 1 number from 1 to 49. A player wins a minimum award of $600 by correctly matching 3 numbers drawn from the white balls and matching the number drawn from the gold ball. What is the probability of winning the minimum award? Since it asks for a probability, we know that our answer is a fraction. The denominator of the fraction is the total number of ways we can pick this lottery number. So when we look at lottery, we're going on the assumption that order does not matter, so we have combination. First thing I have to do is pick 5 from 52. So that would be 52 combination 5. And means I'm multiplying. 1 from 49 would be 49 combination 1. Altogether, I'm picking 6 numbers though, right? To get this prize, I have to match 3 of these 5. So that would be 5 combination 3. But if I'm only matching 3 of 5, does it make sense that 2 don't match? And so there are 52 numbers, and there are 5 that match, which tells me there are 47 that don't match. And so I have 3 that match, and from the 47 that don't match, I have 2. Then I have to match the one winner from the 49. So that I have to come up with all of the different ways that I can get 3 that match, 2 that don't match, and then the one winner from the 49. Does that make sense?
Yeah, I think so.
Okay.
I'll try it
And
again.
usually what makes this question tricky is remembering that I'm still picking 5. So if 3 of the 5 match, 2 of the 5 don't. Are you all right if I leave it just set up like that? What I would do is I would find all of the combinations in the numerator and multiply them out.
Mhm.
All of the combinations in the denominator and multiply them out, and then try to reduce the fraction.
Yeah.
All right?
Okay.
Better?
Yeah, I'll try it again later.
All right. This one is a challenging problem. Should I make this one extra credit? What do you guys think?
Yes. Yes.
Yes? Okay, so what I'll do is I'll go through, and at the end, I will, somebody remind me, please, on Friday when we meet, that I promised that I'd give everybody extra credit for that one question. All right?
Okay.
So I'm going to clear this and ask, does anybody want to look at any of the other questions from this assignment or any other assignment?
Could we look at question 25 from homework 11?
Sure. Homework 11.
Yes, please.
Question 25. This is taking its time. And I think my computer's going to take its time because my daughter and son-in-law are still here with the baby. And so they're watching the television, which is, we got rid of cable, so it's on the Wi-Fi, and they all have phones on. So I think we're stretching the family Wi-Fi a little bit. We'll see how this works. Okay, question number 25 says, it's computed that when a basketball player shoots a free throw, the odds in favor of his making it are 21-6. Find the probability that he misses it. Out of every 100 free throw attempts, on average, how many should he make? Well, with this one, we've got a couple of things going on. And I like that you asked this question because this is kind of picking up with one of the ideas that I wanted to start with. If the odds that he make it are 21-6, remember we said that the probability that he makes it is the first number over the sum of the two, which would give me 21/27. And because I like working with smaller numbers, I'm going to reduce this by taking out a factor of 3 to get 7 nines. So the probability that he makes it is 7 out of 9. So the probability that he misses it, well, if he misses it, it means that he does not make it. And remember, to find the probability of something that does not occur, we subtract from 1. And so the probability that he does not make it is 2 nines. So far, so good.
Yes.
Wait, no. How'd you get 2/9 from 7?
Okay, there are two ways of doing this depending on whether you see the glasses half empty or half full. When I've got that 1 minus 7/9, Adam, do you remember that in order to subtract the fractions, you have to have a common denominator? So to start
Yeah.
with, I'm going to think of that as 1 over 1. My common denominator would be 9, which gives me 9 over 9 minus 7 over 9, which is where I get that 2 9s.
Oh,
Okay, better?
okay. Yeah, that makes a bit more sense now.
Okay, so the probability that he misses it is 2 out of 9. And so if he takes 100 shots, and we're going to say that he misses 2/9 of that, how many should he make? Let's see, if I take 100 times 2 divided by 9 would give me 200 over 9, would give me 22.2 repeating. And so I would think that they, excuse me, folks, I would think that they would have you round that to the nearest whole number. So you'd expect him to, oh, this is he misses 22. If we want to know how many he makes, I'm sorry, how many he makes would be 7/9 times 100, which would give me, I misread that question, he'd make about 78 rounded. Right? How many should he make? 70. I apologize, I misread that the first time. That's what happens when I take my glasses off. But I have to take my glasses off because they're too dirty to see through. Sorry about that, folks. Better? I think, was that Sonia who asked that? Was that better? Huh?
Yeah, thank you.
All right, does anybody want to look at any others?
Can you do the last one for this homework?
Sure. Can I clear this?
Yes.
And turn my finger back into a mouse and go to the very last question. On New Year's Eve, the probability of a person driving while intoxicated or having an accident is 0.3. If the probability of driving while intoxicated is 0.28 and the probability of having a driving accident is 0.09, what's the probability of having a driving accident while intoxicated? Now, this is fun because when I look at this, I see that that original probability has the word or in it. Can you remember that we had stated that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both occurring at the same time? Does everybody remember doing that? We were talking about, let's say, a deck of cards. What's the chances of getting a jack or a heart? Okay, jack is 4 out of 52. Hearts are 13 out of 52. But I have to remember that one card, the jack of cards, is being counted twice, so I have to subtract it out. Does everybody remember that line of reasoning? Hearing silence, I'm hoping that means you do. So the probability of, if I say that A is being drunk and B is having an accident, the probability of being drunk or having an accident is 0.3. Well, the probability of being drunk is 0.28. The probability of having an accident is 0.09. And we're looking for what's the probability of both of them occurring. So I'm going to call that X. This gives me 0.3 is equal to 0.37 minus X. And then we can go through and subtract the 0.37 from both sides to get negative 0.07 is equal to negative X. And so dividing by -1, we get that the probability of being both drunk and getting in an accident is 0.07. I was on a roll there. I apologize. I might have done that a little bit fast. Once I get solving an equation, It's just so much fun. I can't slow down. Did everybody follow that all right, or do you guys want me to redo that in slow motion instant replay? Everybody all right with this rule? The probability of A or B is the probability of the first plus the probability of the second minus the probability that they both occur at the same time. And in this problem, that's what we're looking for, the probability that they're both occurring. We know the probability of A or B is 0.3. The two given probabilities are 0.28 and 0.09. And again, we're wondering what would I have to subtract to make that equal? I'm going to do this addition. And then to solve the equation for x, the first thing we have to do is get x alone on one side of the equal sign. So we'll subtract the number from both sides. So that gives me negative 0.7 is negative x. We don't want negative negative x. We want plain old x. So we'll divide by negative 1 and get x is 0.07. Better?
Yeah.
Yeah.
Yeah. When you see or, it's that or rule. Remember, with or, nothing counts twice. So we add the two separate probabilities and subtract the overlap. And what I liked about this question, the reason I put this question in the homework, is it makes use of that rule, but it makes use of that rule in a way that hopefully makes you think a little bit about it. And my goal with the homework is to make you think. So there you go. Better? I'm going to clear this one then and ask any other questions.
What's gonna be on the quiz? Like, what is gonna be about?
The quiz only has 2 questions on it. It's a probability quiz. They're like questions in homework 10. The probability with the probability with combinations and permutations. All right.
Wait, so just 2 questions, one on permutation, one on combination, or?
I picked the 2 questions about a week and a half ago. I don't remember if one is permutations and one is combinations. I don't remember, but they're
Okay.
just those more involved probability questions, like on that worksheet that we did together in class, like the problems in homework 10, but I promise none of them are as involved as the gold ball lottery question. All right?
Okay.
Oh, yeah. I drink today.
Okay.
However, your project for this unit is kind of interesting because it's going to take what we look at next, the expected value, and take some real life lottery games and ask you to figure out the expected value. So, sort of interesting. Okay, then if that's all right, let's start by, we just did a real 30-second review of turning odds into probability in that long homework question that we asked. And so next place that I wanted to go was the idea of independent events. And what we're going to say is, if the occurrence of one event does not influence the occurrence of the other event, we say the events are independent. So, do you guys need for me to wait a minute till you get all of that down?
Yes.
You ready?
Yep.
What if I toss 2 coins? The first one can be a head or tails. The second one can be a head or tails. Does the outcome on the first coin have any effect at all on the outcome of the second coin? You toss 2 coins. Does the first coin at all affect the second
No,
one?
it does not.
No.
Those are independent. Let's look at another example. Let's say I roll 2 dice. Does the number on the first die at all affect the number on the second die?
No.
No, so they're independent. And what's going to be interesting is if 2 events are independent, I'm going to give them names for lack of originality, A and B. If they're independent, the probability of A and B is equal to the probability of A times the probability of B. If the probability of one occurring and then the other occurring is the probability of the first one times the probability of the second one. We multiply. And that's kind of what our counting principle had told us if we're looking at sequential events. That word "and" told us to multiply. So let's look at a few examples. Let's say I toss 2 coins. What's the probability? They're both heads. Well, the probability of a head and a head, because we said that those 2 coins are independent, is equal to the probability of a head on the first one times the probability of a head on the second one. So what are the chances of getting a head on the first one?
50.
50.
1 and 2.
I write it as a fraction, 1/2. Probability of a head on the second one is 1/2. So when I multiply, my final answer will be 1/4. Another example,
Mhm.
let's say a family has 4 kids. What's the probability? They're all girls. Well, not gonna lie, I'm not a geneticist, and so I'm gonna oversimplify this. Is everybody all right if we say that when a child is born, the probability of it being a girl is 1/2?
Or I guess.
Yes.
And now the gender of somebody's first child has absolutely nothing to do with the gender of their second child or their third child. So these are all independent. So with these 4 kids, we're asking what's the probability if I have a girl and a girl and a girl and a girl. And they're all independent. And so that would be the probability of girl times the probability of a girl times the probability of a girl times the probability of a girl, or a half times a half times a half times a half. Does everybody remember when you multiply fractions out, you're going to multiply across 1 times 1 times 1 times 1 is 1, and then 2 times 2, 4 times 2 is 8, times 2 is 16. So 1 out of 16 of those families would be all girls.
Okay.
Now, I want to look at, and I apologize, it's in the wrong place. On the handout that's attached, we're going to look at number 25. This is conditional probability examples. And number 25, let me make it a little bit bigger for you. It says the probability that South Florida will be hit by a major hurricane, category 4 or 5, in any single year is 1/16. Now let's stop and think about it. If they had a hurricane last year, does that have any bearing on their weather this year?
No.
Does their weather this year have any bearing on their weather next year? No. So we're going to say that each year is independent of the other. And so part A, we ask, what's the probability of getting a major hurricane 2 years in a row? Because they're independent, the first year is that 1/16, that second year is that 1/16, and so we're going to multiply 1/16 times 1/16, and that's going to give us 1/256. What's the probability they get a major hurricane 3 years in a row? That would be 16 times 1/16 times 1/16 again. And so, whoops, this pen's not writing for me. That gives me 1 in 4,096. Well, that's not too bad. Want to move to Florida, guys?
Well,
Now, next one's a little bit dicier. And I think this one in my lab, they'll ask for it as a decimal. So let's find a decimal to the nearest. Let's find it to the nearest 1,000. This says not have a hurricane. Well, if the chances of getting a hurricane are 1 out of 16, what's the probability of no hurricane?
15 out of 16?
Is everybody in agreement? I like that
Yeah.
answer. Okay, so for each year, it's 15 out of 16. And how many years are we doing this for?
10.
So is everybody all right? I can just say that that's 15 over 16 being raised to the 10th power.
Okay.
I'm going to be lazy doing this on my calculator. I'm going to open parentheses. I'm going to type 15 divided by 16. I'm going to close the parentheses. Then I'm going to carry it up from my exponent and raise it to the 10th power. And when I work that out, I get 0.524.
Can you show us how you use the calculator?
Yes. With my calculator, I'm going to shrink this down a little bit. With my calculator, what I did was I opened parentheses. For my fraction, I took 15 divided by 16. I closed my parentheses, and then I used that caret up to get an exponent, and I raised it to the 10th power. Some of you might not have a caret up button. You might have like a y to the x button or something like that. And if you don't like
Where-
doing it all in one
Where
fell
is that
swoop,
button?
which button?
The one you pressed after you closed it up.
The arrow up?
Oh, the arrow up.
Yeah. If you don't like doing it all at once, you can go 15 divided by 16 equals, and then with the number that shows, just do your arrow up 10, and it raises your last answer to the 10th power. Either way, you should get that same answer.
Got it.
But what's interesting about this one is what's the probability that they'll get hit by a major hurricane at least once in the next 10 years? Well, I'm going to go back to the notes for just a second. That was a really long one on page, so I'm starting a new page. What does it mean at least once? Doesn't that mean one or more?
Yes.
So for example, if I have at least once in 10 years, couldn't it be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10? Oh, my head hurts.
Mhm.
4 tells me I have to add all of those probabilities. So I'd have to find the probability of 1, and then the probability of 2, then the probability of 3. But now wait a minute. 1 through 10, isn't that all the possibilities except none? Right? That's the only possibility we're missing, the possibility of 0 hurricanes. And so we're going to find that the probability of at least once, it's the complement of none. So it will equal 1 minus the probability of none.
So just 1 minus 0 then?
Well, no. At least 1 in the next 10 years, that would be 1 minus the probability of none in 10 years.
Mhm.
And so wouldn't that be 1 minus, wasn't that our last answer, the probability of none in 10 years? So that's going to give me 0.476.
Oh.
And remember when we talked about that not meaning subtract from 1, that it was an interesting method. But you know how I had said sometimes that to find the probability of something not occurring, so finding the opposite and subtracting from 1 is sometimes a lot quicker. So let's look at the next one, number 26. This time it says the probability that a region will flood in any one year is 1/10. So how are we going to find the probability of flooding 2 years in a row?
10 over 10.
times, oh Lord, this thing is not liking me today. Times 1 over 10 would give me 1 over 100. Three years of no floods. 1/10 times 1/10 times 1/10 would be 1 over 1,000. No flood would be 1 minus 1/10 or 9/10. So no flood for 10 years would be 9/10 to the 10th. Giving me, is anybody else getting 0.349? And so lastly, the probability of at least 1 in 10 years would be 1 minus the probability of none in 10 years would be 1 minus 0.349 or 0.651. So far, so good.
Yes.
If so, I'm going to go back to where we were and look some more examples of compound events. Next example, let's say I have a deck of cards. I pick one. Then after I pick it, I replace, shuffle, and pick another. If I'm replacing and shuffling, is everybody all right that these would be independent? So if I want the probability that they're both aces, that would be the probability of an ace for the first one times the probability of an ace for the second one, or 4 out of 52 times 4 out of 52, at which point sometimes I think it's easier if you reduce before you multiply. 4 out of 52 reduces to 1/13 times 1/13 gives me 1 over 169. Same problem. Deck of cards. I'm going to pick 2, but not replace. If I want the probability that they're both aces, the first ace is 4 out of 52. But that second ace, if I did not replace my first card, there aren't 52 left in the deck, are there?
No.
No, 51.
There's only 51. And if that first one was the ace that I wanted, there aren't 4 aces left, are there?
Hooray.
Mhm.
So that's
No.
out of 51. And so these are not independent. The first ace changed the probability of the second one being the ace. And so here, they're
So when they change, it's independent?
they're dependent.
Oh, dependent. Oh, not, oh, it says not independent. Okay, okay. My bad.
So the first one would be 1/13. The second one, if I reduce that, is 1/17. And so, oh Lord, I should be able to do 13 times 17 in my head, but I'm being mentally lazy today. So that's 1/221. And do you notice that the probability changed? And so that gives me that idea of conditional probability. And we define P, and it's written B/A, and that's the probability of B given A already occurred. And if A and B are not independent, the probability of A and B, that compound event, will equal the probability of A times the probability of B given A occurred. And I know that looks really fancy and involved, but it's what we did up there with the cards. The first card being an ace was 4 out of 52. But if the first card was the ace, the probability of the second card being an ace is no longer 4 out of 52, but rather it's 3 out of 51. And when we look at conditional probability, sometimes we look at the word given. And the word given tells me I'm restricting my sample space. So let's say, for example, I have a deck of cards. I'm going to pick one. Let's find the probability. It's an 8 given. I know it's a number card. And so over here, because I know I've got a number card, when I make my probability fraction, I know there are 4 8s. But this deck is not 52 because I'm only looking at the number cards. And so instead, that's going to be 4 out of just the number of numbered cards or 1-9. And, oh, dang it. What I was hoping for was that we had more than 2 minutes left, and I was going to look at a lot more of the conditional probability examples. So we'll stop here. We'll do more conditional examples next class. And so that'll be a handout in Blackboard if anybody wants the Blackboard handout to work along with. And also, we're going to be looking at expected values. And that's also going to be a handout in Blackboard.
Okay.
And so if you want these word problems printed up in advance, pardon me, you can do them that way. Otherwise, I will definitely include the handouts in the notes. I think that probability, conditional probability examples has been tagged along for a while. So we'll
Okay.
finish that next class. I'm sorry, I must have been talking too slow today.
No, you're fine.
I'll try to talk faster next time. Really well. No. Is this everybody following along with what we've done today?
Well enough, I guess.
I think so.
All right, well, I'm gonna stop recording.